We're going to now look at our first shortcut for doing derivatives without using limits. I'll support why it works using limits, but then after that we just need to know the rule so we can do derivatives more quickly. So in this video, we're going to look at the derivative power rule, and polynomials. Okay, how it applies to polynomials. So the first thing I'm going to do is I'm going to state the rule, because that's really the big thing we need to get from this video is what the rule is, and then I'm going to show you why it works, and then we'll do some examples applying the rule so you can get comfortable with the different applications. So the power rule is probably one of the ones you're going to get the most comfortable with, one of the most basic derivative rules there is. The power rule says if you have the derivative, let's say we're working with x, if you have the derivative with respect to x of x to some power n, right, x to some power n, then the way to take that derivative is to, and I'll walk you through the process here, how to sort of mentally, or how to visualize this rule. So the first thing you do when you're thinking of the power rule is you take the exponent and you drop it down to the front of the x and turn it into a coefficient. It's very similar to a logarithm property that you may have learned, or a logarithm law, depending on your terminology. Taking the exponent and moving it down to become a coefficient. So if we do that here, if I take the exponent, by the way, the variable here is x, right? Because I'm taking a derivative with respect to x. The x is the variable, n is a constant. Okay, so keep that in mind. If I take the derivative with respect to x, this exponent comes down to the front and turns into n as a coefficient. And then after you do that, so you have n times x, and the exponent up here, when you take it and move it down, the exponent here decreases by 1. So you take away 1 from the previous exponent. So what that means is the exponent here is now 1 less than what it was before, so it's n minus 1 as your exponent. Okay? So we're going to look at this rule. We're going to do some examples with it later, but it's one of the most basic rules. If you want the derivative of x to a power, or whatever your variable is, to a power, you drop the power and lower it by 1. Now the really cool thing is, this is true for any real number n. So n can be any constant. It doesn't matter what it is. It could be a square root, it could be e, it could be pi, could be negative, could be a fraction, could be a decimal. Any of those cases, this property will work. Okay? We're going to look at why it works in the most basic cases. Just because there's some interesting algebra that happens there that you should probably see as a calculus student, at least for now. So let's explore this a little bit. If I want the derivative of x to the n, and I want to find it using limits, then I would do the limit as h approaches 0 of the quotient f of x plus h. In other words, plug x plus h in for x. So I get x plus h to the nth power for my function. This is n, that's h. Minus f of x, well that's just x to the n. And that's all over h. Now the cool algebra that I was talking about involves the generic expansion of x plus h to the n power. So I'm not going to teach all of the theory behind this, but I am going to help you see kind of what happens here, and we'll see how all of this turns into this outcome. So the first thing is, if we go off and explore this, if I have x plus h squared right? If I take x plus h times x plus h, here we're looking at the n value of 2. You'll get 1x squared plus 2hx plus 1h squared, okay? All right, so pretty interesting. Some patterns that are happening here is your first term is this guy squared, your last term is this guy squared, and your middle term is a combination of h's and x's, okay? We'll point out some other patterns as we look at some others. If I look at x plus h to the the third power, sometimes I can count correctly, x plus h to the third power, I get 1x cubed, and on the end I get 1h cubed, so similar pattern to this guy, right, with the first and last terms. And in the middle terms, I'm going to get different combinations of x and h. So how does that work? Well, my second term here is going to be, the x power is going to be 1 less than it was. So it's going to be, I'm going to leave a space here for my coefficient. It's going to be x squared, and the h is going to be h to the first. So every term up here has a degree of 2. So here I've got x squared, here I've got h to the first, x to the first, that's a degree of 2, and here I've got h squared, that's a degree of 2. In this case, every term is going to have a degree of 3. So x cubed, and then I lower my power of x by 1, so it turns into x squared, but to get a degree of 3, I have to throw an h in the mix. And then I'll have plus some coefficient, lower the power of x to make it x to the first, to make it power of 3 total, degree 3 total, I'll make this h squared. And so that's kind of the pattern for expanding these binomials to a power. And so it happens to be that the coefficients here are 3 in this case. Okay? So that's pretty interesting. I'll talk more about the coefficients as we proceed. If I look at x plus h to the fourth, I'm going to have 1 x to the fourth plus a coefficient times x cubed h plus a coefficient times x squared h squared, plus a coefficient times x to the first h cubed, plus a coefficient 1, we know the last coefficient's 1 h to the fourth. Okay? So same pattern where you lower the power of x by 1, but you keep the degree 4 on every term, and the coefficients here happen to be 4, 6, 4, and then 1 there at the end. Now, what I want to point out, what I want to emphasize is there's lots of cool things happening here. So, for example, I'll just point out this pattern in case you're interested. The 3 here is the same as 1 plus 2, the sum of those coefficients. And this 3 is the same as the sum of 1 plus 2. This 4 is 1 plus 3. The 6 is the 3 plus the 3. And this 4 is the 3 plus the 1. And so if you want to keep getting higher powers, you can keep doing that pattern to get your coefficients, and you always start and end with a coefficient of 1. So that's pretty fascinating. If you want to look more into that for your own purposes, for your own interest, you could look up something called Pascal's triangle. Okay? And it's the same pattern, and you can get into some counting techniques called combinations that will tell you how to get these coefficients as well. So if that piques your interest, go take a look at that. But what I want to get into for this video is the cool thing that we're going to use is that the coefficient of the second term is the same as the exponent here every time. Okay? So that's kind of what we have to establish if I want to look at x plus h to the n power. So if I were to apply this, x plus h to the n power, right? I'll have x to the n as my first term, and I'll have h to the n as my last term, just like we had up here. But then the pattern in between is going to be, well, the coefficient of my second term is going to be the same as this power. So it's going to be n times x to a power, and I have to lower the power of n by 1. So that's x to the n minus 1. But now, because I need this whole thing to have a degree of n, and I've taken one of the n's away here, I have to put h to the first next to it. And then my next term is going to be some coefficient, we don't care, you'll see why shortly, some coefficient times x to the n minus 2 times h squared, plus etc., etc., etc. Okay? So the key here is following this pattern, knowing how to get the coefficient of your second term, and then the last thing is noticing that that all of these terms after the first term have an h in them. All the terms after the first term have h. Okay, so keep that in mind. So let's come back over here and apply this. So this guy turns into the limit as h approaches 0 of, if I expand this, it'll be x to the n plus n times x to the n minus 1h plus other terms. Here's what I'll do. Other terms with h squared or higher. Okay? So this is h to the first. Every time I go to the right, the power of h is going to go up. So that's this guy here. That's the x plus h to the n, right? Let's use brackets there. That's my x plus h to the n power. And then I still have to subtract x to the n. And that's all over h. Okay, so I'm trying not to be terribly technical here. I certainly could be with this. But I'm just going to emphasize what we need here. Calculus 1 may be the first course you've taken with a lot of technical mathematics, and so I don't want to overwhelm you, but I want to get the point across. Now, what happens when we simplify the top? Well, we have x to the n minus x to the n. That's 0. Awesome. Now, here's the cool part. The h on the bottom, every term that remains has an h, like I said over here. Every term after x to the n has an h. And since x to the n canceled, I don't have to worry about that. So what I'm going to do now is I'm going to cancel this h with the h in all of these terms. So this h is going to go away, and all that's left is this guy, n times x to the n minus 1. And everything here, when I cancel my h, since he's had h squared or higher, when I cancel this h with an h in each of those, I'm still going to have an h. I'm still going to have an h left, okay? So keep that in mind. So what this turns into is the limit as h approaches 0 of n times x to the n minus 1 plus, let's call them h terms. They all have an h left, right? So now, because h goes to 0, my h terms, every term that has an h in them is going to go to 0. And so all that remains of this limit, is n times x to the n minus 1. So the derivative with respect to x of x to the nth power is n times x to the n minus 1, which is the power rule. Okay, so that's pretty interesting. I hope you like this sort of expansion with binomials. You could also reference the binomial theorem describes this process in its entirety. I can't believe I didn't mention that before. So there's this intimate connection between binomial theorem and Pascal's triangle dealing with these polynomials. Now, what we did was we looked at is when the exponent n was a whole number, okay? A positive integer, a natural number. The cool thing about the power rule, though, we can't see it based on this because we were assuming whole numbers or positive integers here, is that the power rule applies for any real number n. And we may look at that later on. You can see it using some logarithm stuff, but we're not quite ready yet. But this is the power rule. And now that we've seen why it works and we know the rule, let's practice with the rule so we can get a better handle on it. Because it will apply in some situations where you may not think to apply it. But we'll start basic. Okay. So let's say we want to do this example where let's determine, and I'm going to switch variables now so we're not always working with x, so we can start to get used to this Leibniz notation. Let's say I want to determine d dt of, how about 3 t squared minus t plus 4. Okay. So I want to differentiate this function with respect to the variable t. So t is my variable now. Well, this is a sum and difference of power rules. And you've got a constant multiple of this function too. So really what you can do, let me use a different color. Really what you can do, you can skip all of this eventually, but I'm going to show you one time. Because you've got a sum and difference and a constant multiple here, what you can do is you can push the derivative into the functions of t. So you've got d dt, sorry, let's pull the constant out to the front of this derivative. So it's 3 times the derivative with respect to t of just the t squared function minus the derivative with respect to t of the t function plus the derivative with respect to t of the constant function 4. Now that one we're going to talk about a little bit. But now all we have to do, because we've got derivatives of powers of t, we can use the power rule. So here I'm going to take 3 multiplied by, we'll take the exponent, move it down to the front. So I've got 2 times t, and then lower the exponent by 1, so it's t to the first. So I've got 3 times 2t to the first. Minus, same thing here, the exponent's 1. So move the exponent down to the front, so that's 1. We don't have to write that. So it's 1. I'll write it out this time, I suppose. 1 times t, and then I lower the exponent by 1, so it turns into t to the 0. Okay, so we'll simplify this shortly. Now, the last guy, 4, one way to think of it is, if you thought of it as a power rule, it'd be 4 times t to the 0, because t to the 0 is 1. And so if you differentiate the t to the 0, so your constant moves down, and you're going to move your coefficient down to the front, so it's going to be times 0 t, and then the exponent lowers by 1, so it turns into negative 1. But because it's all multiplied by 0, the derivative of this whole thing just turns into 0. In fact, we could make another rule about differentiating a constant. So this one's very basic. The derivative with respect to any variable, let's say x, in this case it's t, of a constant is always 0. And that totally makes sense. If you graph a constant function, it's a horizontal line, and the derivative, remember, is the slope of the tangent line. Well, the tangent line on this is always horizontal, so its slope is 0. So the derivative of any constant is always 0. So this turns into plus 0. Now let's simplify it. 3 times 2t to the first is just 6t, minus t to the 0 is 1, plus 0. Okay? So the derivative of this function is 6t minus 1. Now, eventually, you're going to jump right from here to here. And so that's what I'm going to kind of do as we proceed with more examples. We don't need to show all this extra stuff here showing how we're doing it. The goal is to make this quick. All right, let's look at maybe 2 more examples that are more interesting now that we have the basics down. I'll rephrase the language as well each time. Let's say differentiate. How about f of x equals, and let's look at 2 times the square root of x minus 4 times the cube root of x. Okay? So you might be asking yourself, well, I don't see any powers here. How can I use the power rule? Well, square roots, cube roots, roots in general are exponents. So in other words, f of x, we could rewrite f of x as 2, and the square root of x is the same thing as x to the 1/2 power. Minus 4 times the cube root of x is the same as x to the 1/3 power. And then when I differentiate, I'll differentiate both sides. So I'll take the derivative, meaning now I'm going to say f prime of x. So see, I'm trying to switch notation and language a little bit. to familiarize you with all the different ways you could say this. So rather than showing all those unnecessary steps we had before, they were necessary then so you could get comfortable, but now we're just going to skip over the constant and we're going to jump right to the function. So I'm going to take my 1/2 down to the front. So I've got 2 times, and this turns into 1/2 x, and then my exponent lowers by 1. If I subtract 1 from 1/2, I get negative 1/2. So that's 2 times 1/2 x to the negative 1/2 power. Minus 4 times, move the exponent down, so that's 1/3 x. Lower 1/3 by 1, which makes it negative 2/3. And so we end up with f prime of x equals, well, 2 times 1/2 is 1, so this turns into x to the negative 1/2 minus 4/3 x to the negative 2/3. And so you could do all kinds of things with this now. You could leave it like that, but you could go further and you could do things like, well, this is a negative exponent, so that means take the reciprocal, so that's 1 over x to the 1/2 minus 4 over 3. This is a negative exponent too, so it could go on the bottom and become x to the positive 2/3. You could leave it like that. You could go further as well and convert x to the 1/2 back to a square root. So this turns into 1 over the square root of x minus 4 over 3. Turn this back into a cube root, so it'd be the cube root of x squared, right? Dealing with your exponent properties. And so you can really do a lot with this. You could try to rationalize the denominators if you want to. It's unnecessary. But all of these are correct answers for the derivative of this function, and they just use the power rule, okay? So get comfortable with the power rule when your exponent is not an integer. Okay, let's try one more where we'll throw all kinds of things at you. And you may want to pause and try to work this out on your own before I show you. So let's use different language one more time. Okay, so determine g prime of t. We'll use g and t, and we'll use the prime notation here instead of saying differentiate. Determine g prime of t if g of t equals, and we'll turn it into a fraction. So let's say we've got 3t squared minus 6 times the square root of t all over t to the 6th, let's make it the 5th power, okay? And so the temptation here might be to take the derivative of the top, like we've been doing, just this difference, divided by the derivative of the bottom. You can't split derivatives across quotients. You can only split it across additions or subtractions, okay? So what we have to do here is rewrite this g of t function as a sum or a difference only, no quotient. So what we can do is we can simplify this function. I can divide this term by t to the 5th. So when I do that, t squared over t to the 5th, well, that's going to leave that 3 on top, and it's going to leave t cubed on the bottom. Okay? Minus, well, this guy is, let's write it out, 6 times t to the 1/2 over t to the 5th. And we can simplify that also. So we've now split our quotient to be a difference, which is crucial to differentiation. At this stage anyway. We'll learn how to differentiate quotients later on. All right, let's keep going. Let's keep simplifying. Well, this guy here is the same thing as, if I'm dividing by t cubed, that's the same thing as times t to the negative 3rd power. And now I've got a power of t that I can differentiate. Over here, I've got 6. And again, I subtract my exponents. 1/2 minus 5 is t to the negative, 1/2 minus 10 halves is negative 9 halves. And now I've got t to a power as well. Now the power rule is a piece of cake. g of t equals, and I'm going to move my exponent down to the front to be a coefficient. And another shortcut you can use is because you know when you move this down, it's going to multiply by 3. You can go ahead and multiply. So negative 3 comes down and multiplies by the coefficient of positive 3 to give us negative 9 times t. And then I subtract 1 from my exponent of negative 3 to get negative 4. All right? Same process here. Take my negative 9 halves down, multiply it by my coefficient of negative 6, which is going to be positive 6 times 9 halves is 27, t, and then lower my exponent by 1. So I subtract 1 from this, which gives me t to the negative 11 halves. And I'm going to leave it at that, okay? We'll leave it at that. And I apologize, I forgot to call this g prime of t because it's the derivative of the g function with respect to t. So that's the power rule, applied with some derivatives of sums, differences, constant multiples, and the derivative of a constant function itself. But it's not too bad. Get some practice in with it. The toughest thing you'll find is dealing with roots and quotients and things like that to where you can use the product rule, or sorry, the power rule.